So one of the things we got to do is move around this air that we have around us. You all feel it in the wind every day, and the air doesn't just stay in one location. And there's a lot of influences that go into that, but the main one is pressure. So let's talk about wind and how it influences us and how it develops. So what forces control the speed and direction of the wind? Well, in order to move an object, there must be some kind of force applied to it. When you're moving your car, your wheels start turning. That's a force that's applied to move your car. When you go running, you're pushing a force with your legs to make you move forward or backwards. So there are all types of forces, and forces can move in different directions. But again, it's mass times an acceleration. Mass being the weight of the object, and acceleration being a change in the velocity of the object, a change in the speed. So we're going to apply some forces. What forces are we going to apply? Well, the air pressure gradient is one. We looked at the air pressure gradient earlier, and that is a significant part of what blows the wind. Centripetal force is another. Coriolis, friction, gravity are all forces that work on an air parcel. And by knowing how strong each one is, we can tell you the direction that air parcel is going to move. So, for example, pressure gradient. The closer the isobars are to each other, the stronger the pressure gradient. Air will always flow from highest to low pressure. Again, the atmosphere wants to get rid of low pressure. It wants everything to be uniform. So it is always going to try to get rid of that lower pressure. So if you look at this, the pressure gradient is perpendicular to these lines. It goes like this, right down and towards lower pressure. Here would be high up here, go like this as well. Little further apart, however, so the pressure gradient's weaker. There's another force called centripetal force. When you are driving your car, what keeps you from just going, when you go around a corner, from not constantly going straight and never being able to make a corner? Well, it's something called centripetal force. It holds you in and pulls you around that corner. It happens to air as well when you see air moving in a circle. So the stronger the wind is, the more power you can get to the centripetal force, actually. But it is just like a string holding, as it shows you here, a ball running around in a circle. However, it's not independent. So in other words, it causes an object not to move in a straight line. So it's an unbalancing force. It's constantly changing. That force is constantly changing as you go around the curve. Maybe you have to move your steering wheel just a little bit to make it around the curve. That's because the centripetal force is changing. Coriolis force may be one of the more complex and unique forces we got. All right, the Earth rotates. We know that. We see the sun rise in the east and set in the west every day. The Earth rotates to the east. That's what causes that. So if we have an Earth rotating, and the Earth is much, much further around at the equator than it is maybe at the North Pole, so it stands to reason that the Earth is going to have to move further in a few minutes at the equator than it ever would at the North Pole. That motion, that change in motion as we go up or down, north or south, is called Coriolis effect. In the northern hemisphere, it causes everything to turn to the right. If you were playing pool in the northern hemisphere, it actually is impacted by this Coriolis effect. You take it in automatically, but it is a minute change in how your ball is moving. And you can see here the different Coriolis effects. However, at the equator, Coriolis effect is 0. At the North Pole, it's a maximum. So, I'll give you the example of a guy playing pool again. because it was taught to me that way. And the guy's playing in Alaska 1 week, got a lot of Coriolis effect. He's got to take that into account every time he strikes that pool ball. The next week, the guy's playing in Brazil. All of a sudden, Coriolis force isn't there. He has to make an adjustment. So there is a difference, a different deflection, depending on which way. And oh yeah, in the southern hemisphere, the Coriolis force turns everything to the left. In the northern hemisphere, it turns everything to the right. Friction is another force. When you move along the road, we have rolling friction with our tires. If you put a hand down and try to move along the surface of something, you feel resistance to your motion. That's friction. Air has it. Say air wants to go over a nice flat terrain, it has friction, but it's moving along. Now all of a sudden it's hitting mountain ranges or very, very hilly. That air is going to slow because of friction. There's even friction high up in the atmosphere as well. It's just different, called eddy viscosity or turbulence. Turbulence is just fluid flow characterized by eddy motion. So they form eddies. Turbulence has got to be one of the most complex things to calculate. We can't do an exact calculation on turbulence. The math can't be solved. But if you were to pour a creamer into a cup of coffee, just a couple drops, watch it go in all different directions. That's turbulence. And the equations that have to govern that have to take into account of where that creamer went in every single second, in every direction. And it's just not something that can be done at this moment in time. Gravity is another force. It pulls everything down. It weights everything down towards the ground. So it's always constantly pulling air down at 9.8 meters per second, force of gravity. Oh yeah, there's another part to gravity, and one of the critical thinking questions you're going to get says, what are the two parts of gravity? On a rotating Earth, there's centripetal force, which is much weaker than gravity, but is a part of gravity. So the two of them combine to make gravity. So now we've talked about horizontal pressure gradients, centripetal force, Coriolis friction, gravity. So let's start simple. Why on earth is not all the air come rushing down and hitting us, crashing into us at the ground all the time? Well, remember there's a pressure gradient in the vertical, pretty steep pressure gradient. So if you got rid of gravity, all the air would just fly away because the pressure gradient was that way. But by keeping gravity in, that balance causes an air parcel not to move. We'll define an air parcel as, I don't care, 50 feet of air, 10 feet of air, it's round in a circle. You choose. But that is hydrostatic equilibrium. It means that air parcel has got to move at the same rate up or the same rate down. And if nothing's pushing it, it's going to stay exactly where it is. But it can move up and down. Say an air parcel hits a mountain, it's going to go up the mountain, come down the other side, it might be pushed back down. But gravity and vertical air pressure are balanced in hydrostatic equilibrium. Now, there's another simplification, we call it, called geostrophic wind. Geostrophic wind is wind that eventually is blowing in a straight line parallel to the pressure gradient. In other words, it's not cutting across it. What happens is you start with a pressure gradient, and we immediately have a Coriolis force trying to turn it to the right. Over time, they become balanced. And when they do become balanced, pressure gradient pushes the parcel of the air straight right along the lines. Now we know there are lows and high pressures. We've talked about them. And low and high pressure have another part. That's the centripetal force. So here you have centripetal force, pressure gradient force, and Coriolis effect all balancing each other. So yes, these air parcels are rotating around where the pressure gradient is in a parallel circle to it, but they're being held that way because of the centripetal force. Coriolis effect and pressure gradient force are offset. Each other are equal, but the centripetal force causes them to go in the circle. And the same thing happens in low pressure. When you get down closer to the Earth's surface, there's more friction. Friction plays a role. What does friction do? It reduces wind speed. So if you have less wind speed, your Coriolis force is going to be lower. So instead of going parallel to the isobars, it's going to want to blow outward from highs, partially across the isobars, and inward towards low pressure. There we've talked about convergence and divergence, where air is flowing towards each other or away from each other. High pressure, air is flowing apart because of friction. And here you can see an example of that. And here you can see the continuity of the wind. If you have very strong horizontal wind convergence aloft, it's going to tend to push the air down. We have the horizontal divergence at the ground, sinking air, and high pressure forms. If you have the opposite effect, you get divergence aloft, convergence at the ground, you have rising air. So, we're going to talk about a sea breeze here. A sea breeze forms over the water, we'll say. Over the water is very smooth. There's not a lot of friction. So that air is moving very quickly towards the land. Air is hits the land, the friction's a lot higher. The air is going to slow down. So when it hits that, it's going to tend to rise. And when that convergence develops, the rising motion, and that helps to cause showers or even thunderstorms. At nighttime, the air is coming from the land. Now it hits the less friction over the water. It speeds up. Air tends to sink. That's why in the evening, along a coastline, the clouds tend to dissipate. So, I just wanted to show you a couple of quick things here. I wanted to go back to that same little low we were looking at earlier in the pressure gradient. Notice the winds are always incoming towards the low pressure, just like we talked about. High pressure, they tend to move away. Much weaker. Pressure gradient's a lot less. Here we're going towards the low, pressure gradient picks up, the winds are starting to move inwards. So you can see an example right away of how high and low pressure works. And what you just learned can be taken into account. If you look aloft, here there's very little friction. Winds are going right around, very close to parallel to the, in this case, contours, which are similar to isobars. And yet you can still have gradient wind, not just geostrophic, because they'll move around lows like that or highs. And finally, as you get closer to the ground, you can see the wind flow tends to change. It's weaker for one thing, tends to move towards low pressure and away from high pressure again, more even emphatically than otherwise. So, hope you got something out of all this. Please don't hesitate to ask if you have any questions.